Yeah, what the layperson calls dust, we also call dust, yeah.
You're listening to The Cosmic Cast. Hello, and welcome back to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. As per usual, this week I'm joined by regular co-hosts of Marissa Lowe, Ricky Bahir and Tom Harvey. And this week, based at the Natural History Museum in London, is Martin Suttle. How's it going?
Hello, it's going really well, thank you. I'm making the most of the lockdown by working hard at home and enjoying the sunshine from indoors.
Well, yes. How are you finding working from home?
Well, the kind of work I have is there's very few days of data collection, produce lots of data, which result in lots of time sitting behind a computer processing and writing up that data. So kind of the ratio of in the lab to behind a computer is such that the lockdown is quite, for now, is quite okay in terms of I have lots to be getting on with.
Yeah, well, that's good. So how would you describe yourself then? Would you describe yourself as a geochemist or an experimental?
I would describe myself as a planetary scientist, I guess, which is quite a broad term for studying extraterrestrial materials. But I come at my field as a petrologist, I guess. So I look at rocks under the SEM and X-ray diffraction and that sort of thing. So microanalysis. I like looking at rocks under microscopes, basically.
Yeah.
That's pragmatically what I do.
So did you come to planetary science from a geology background then, or from a different subject area? Exactly,
yeah. So I came to where I am now initially through geology. So I did a 4-year undergraduate geology course at Imperial College London. And that was termed an MSci degree, which is a 3-year bachelor's and then a 1-year independent research master's tagged on the end, and it forms a single degree. And so I did that. And initially, when I started out, I was really interested in all of geology. So I took a broad degree. But within that, I thought I would go on to specialize in paleontology. So I was really interested in life and fossils, and in particular, the creepy crawly kind of fossils from the Cambrian. So like all these marine animals.
All the weird looking ones.
Exactly, yeah. So I was super interested in that to begin with, and read lots around that subject. And actually the book that got me interested in, or convinced me to choose geology for a degree, was a book called Wonderful Life by Stephen Jay Gould, which is about the Cambrian explosion and these unusual fossils that are found in these Canadian rocks. Mm-hmm. But as I came to the end of my degree and I had to choose an independent research master's project, I ended up choosing a project on micrometeorites to do something different. Because by that time, I'd already done a year abroad at Utrecht, the Netherlands, and specialized on climatology and paleontology while I was there. So I sort of had my fill of that. So I wanted to get into a different area. Anyway, so during my independent masters, I did a project on micrometeorites, which is what I ended up studying for then many years thereafter. And micrometeorites are small grains of dust. So they're dust in space, and then they spiral inwards and get captured by Earth's gravity.
So when we say small, are we talking microns?
We're talking anywhere between bigger than 20 microns all the way up to about 3 millimeters. Mm-hmm. So, what the layperson calls dust, we also call dust, yeah. same size range. So I was interested in looking at some of that because that was a project that my supervisor at the time, Dr. Matt Genge at Imperial, offered. And essentially he had a vial of dust from a single mountain in the Antarctic called Lagman Nunatak. And a lot of the project was picking out cosmic dust among all this terrestrial sediment and then putting it under the microscope and trying to work out something about where it came from.
Mm-hmm. That sounds quite challenging, doing that picking.
Yeah, okay. So the learning how to pick micrometeorites is actually not that tough when you have the right sediment. In order to find micrometeorites, everything we do is trying to increase the relative abundance of cosmic dust with respect to the terrestrial sediment. And so this is why we were looking at Antarctic sediments rather than anywhere else. So although cosmic dust falls to Earth all over the Earth, everywhere, at a rate of approximately 40,000 tons a year, so there's loads of it, it gets diluted, as it were, and hidden among all the other terrestrial dust. So to find micrometeorites on Earth, we want to look in places where there's very low sedimentation rates of Earth's own sediment. And in practice, that can be either ice and snow deposits in the Antarctic or in Greenland, or deep sea deposits on the seafloor very far away from continents where there's no or very limited influx of sediment from rivers. Now, we can collect micrometeorites from both of those places, and then some of the earliest micrometeorites ever recovered were from deep sea deposits in the 1870s by the HMS Challenger expedition. But it turns out that sitting on the seafloor for thousands and thousands of years, as before those sediments are converted into rock, results in a lot of the material being dissolved and corroded and lost by the acidic action of the oceans. And so instead, Antarctic sediments, which produce much younger or potentially younger micrometeorites that haven't had that much interaction with liquid water, is a better way to find more particles that are better preserved.
So if you have this vial of dust, how do you then go through it and identify these micrometeorites, and how do you remove them from the rest of the dust?
So the first thing you need to do, which is going to sound odd, is that you clean the dust. So the dust is actually got other dust on it, as it were. And what I mean by that is, so there are grains of silicate rock which are cemented together with salts. And so a lot of these salts are sodium chloride salt, table salt that comes from the ocean that's blown up into the atmosphere in Antarctica and deposited, but also sulfate and sulfide salts. So these are sodium and sulfur-rich compounds. And both of those dissolve in water, and that helps us liberate the grains. So instead of being aggregates of lots of grains, they become individual grains. And so we wash the sediment in either high purity water or alcohol. And alcohol is potentially a better option because if it's 100% ethanol, then you're not actually forcing the potential micrometeorites in contact with liquid water, which is one of these things that we want to avoid if we're going to then go on and study water on asteroids in space and the interaction of silicates and water. So we wash the sediment, and that helps it separate out into finer grains rather than clusters. And then we sieve, once that sediment is then dry, we sieve that sediment because we know that micrometeorites have a kind of specific size distribution that peaks around 200 microns. So that's where most of your particles are going to be.
Is that just to do with how these things enter the atmosphere, I guess?
Potentially, yeah, but also to do with the size distribution of the material that's producing that dust. So those asteroids and comets, which is where micrometeorites come from, are going to produce dust with a distinct size distribution.
Right.
It looks like the majority of the source bodies produce a peak around 200 microns, which is quite fine. And so that leads us to believe, that's one of the lines of evidence that makes us think that a lot of these micrometeorites are coming from fragile, hydrated material that's quite weak.
Okay, that's interesting. So does that imply then that the sort of what you're getting out of these micrometeorites then are not really represented by the larger hand-sized fragments of meteorites that we more commonly associate with studying, I guess?
Yeah, that's a really interesting question, because this is actually one of the fundamental areas of research for micrometeorites, is trying to work out where they come from. And this is what I spent a lot of my time doing. We can approach this question from many different kind of geochemical isotopic solutions. But so it sort of suggests that although lots of the material we find among the micrometeorite flux is represented by meteorites, the two populations are not the same. So that's something, some of the same material, but definitely other stuff which we don't find in the meteorite record. And the most obvious among those is cometary material.
Mm-hmm.
So although we're very confident that the meteorites we have on Earth and we find in Antarctica and we see fall come predominantly from asteroids, we don't think that any of the meteorites come from comets, whereas in contrast, some fraction of micrometeorites appear to come from comets.
Yeah, that's really cool.
Big arguments in our field is the ratio of how much is asteroidal and how much is cometary.
And is this mostly based off oxygen isotope analyses?
So it's kind of a different way you approach the problem, you come to different solutions. So astronomers and numerical modelers that look at the dust bands in space that are spiraling inwards to feed the material that comes to Earth seem to suggest that the majority of that is cometary. So yeah, from a big picture astronomical perspective, it looks like it's dominated by comets. But then from the mineralogical perspective, from people like me who look at the micrometeorites that we find at the Earth's surface, they look more like what we expect of asteroids.
Okay.
And this problem is our boundaries and distinctions and whether asteroids and comets represent a spectrum of material.
Yeah.
And part of that is also probably the atmosphere, Earth's own atmosphere, biasing the flux preferentially towards asteroidal material. And the reason that would be the case is because the probability of survival as a particle comes in through the Earth's atmosphere is very largely dependent upon its speed. And cometary material will come in at much higher speeds and therefore burn up, is much more likely to burn up than asteroidal material.
Yeah.
So
sorry, go on.
I was just going to say, it could be largely an effect of just Earth's atmosphere.
Yeah. Does water content make a difference too? Because I suppose if you've got something that's got a high water content coming from the atmosphere, does that flux it and help it burn away in the atmosphere, I suppose?
That's absolutely right. So material that's rich in water is actually much more likely to survive through the Earth's atmosphere than anhydrous, than dry materials. And the reason is that water is a very efficient absorber of heat. It has a very high heat capacity. And so that means you need to put in a lot of heat energy in order to heat the particle up. So compared to something that's dry, you need more heat energy to reach the same temperature. And as a result, that helps them survive. Effectively, by boiling off that water, they are able to maintain lower peak temperatures.
So you get this dust and sorry, Melissa, you go for it.
I feel like we're about to ask the same question.
Yeah, you go for it.
I was going to ask, so once you've separated out your micrometeorites from your other dust, what techniques are you using to study them, and how much does the tiny size of these micrometeorites affect your analysis?
So the size is really critical, and it's one of the big drawbacks, of course, because the smaller a particle is, the less you can do with it. With a larger meteorite sample, we can break a piece off and we can send that piece for some destructive studies, and we can break off another piece and set that up in a polished block and put that in the SEM, etc., etc. With a micrometeorite, you obviously have a very limited amount of material, and so you have to be very careful about how you're going to treat that and what techniques you're going to use. Pragmatically, the vast majority of micrometeorite researchers embed the particles in a resin and then section the particles so that we can see in the interiors of these materials. Then we put them on the SEM, under the SEM. So that's a scanning electron microscope. And that allows us to see the textures and the mineralogy and the chemistry of the particles in a largely non-destructive way. And from there, we might then sub-select a series of particles which are more interesting than the rest for whatever reason, and then potentially direct those towards a more destructive type of analysis, like nanosims or ion probe or something else.
And if part of your research is to try and figure out where this material originated from, if you're looking at a sample, so say you've got this vial and you've separated out all your micrometeorite material, how much of that material has been mixed from other sources? So say, for instance, do you expect that all to come from one body, or is it likely that lots of different bodies have mixed their dust as it falls through the atmosphere? So you're actually looking at lots of different sources.
We're definitely looking at lots of different sources, which is what makes it a big problem. And to be clear, we're not trying to say that this individual particle came from that specific asteroid. It's more like we want to say that this particle came from this group or family or that sort of thing. So we can look at the mineralogy and the petrology and the oxygen isotope compositions of micrometeorites, and that gives us clues to where these particles are coming from. But in the same vein, we can also look out into space and look at which bodies are producing dust, and that also helps us limit the number of potential bodies that these things are coming from. Mm-hmm. There are two main supplies of dust to Earth. One of them is from comets. So as comets come close to the sun, they heat up and they essentially evaporate or sublimate material, and that releases dust. And they produce very distinctive dust streams. And as those dust streams intersect Earth's orbit, we get meteor showers. And so throughout the year at night, you get these regular meteor showers, the Perseids and the Geminids. And we actually know which bodies they come from. And those are definitely sending micrometeorites to Earth. On the other hand, in the asteroid belt, over very long timescales, those asteroids collide with each other, and that causes them to break apart in these very big catastrophic collisions. And that generates loads and loads and loads of dust. And likewise, that dust spirals inwards and is captured by the Earth. So in terms of asteroids producing dust, there are three specific families that we think are very strong candidates for supplying micrometeorites to Earth today. And of those, two are what we call C-type asteroids. So that designation is based on the spectral class of the asteroid. And they're associated with carbonaceous chondrites, so primitive, potentially hydrated, maybe outer solar system material. Whereas one of those groups is an S-type asteroid family, which is called the Carbonaceous asteroid family. And that's probably associated with ordinary chondrites, which are more anhydrous, coarser-grained, inner solar system material. So in answer to your question, we're definitely getting material from many different sources, and it's all mixed in over time, but there's probably a few dominant sources.
So probably, go on, Tom.
So what I was going to ask is, relating to kind of ordinary chondrites and carbonaceous chondrites, people might have seen, thin section photos or backscatter electron images. When it comes to looking at kind of micrometeorite material, how recognizable is it when kind of petrologically, mineralogically, when compared to larger samples of the same material?
So this process of the particles coming in through the Earth's atmosphere is really important, and it changes the micrometeorites significantly. This is because those particles are heated up to maybe up to 2000 degrees and cool back down again in a space of usually less than 10 seconds. And that means that a lot of the particles melt. When they melt, they pull themselves into little droplet shapes, and we call them cosmic spherules. And the vast majority of the micrometeorites that we find are these cosmic spherules, maybe 90% of them. And because they've melted, we no longer have the textures or even the original minerals that they had on their parent asteroid or comet. But they do preserve the geochemical signatures, so the same chemistry, and they do preserve the oxygen isotopes of their parent bodies. And in some of those melted particles, they're not 100% melted, so there are relic grains. I mostly study the unmelted fraction, so those particles lucky enough to come in through the Earth's atmosphere at speeds and angles low enough that allow them to survive unmelted. And even if they are unmelted, they're probably still heated to some degree, maybe 600-700 degrees. And that might change the organics inside those particles, but it will leave the mineralogy the same. And it's in those particles that we can then look at and say something about the textures and mineralogy of the parent bodies. But in answer to your question, how do we know that an unmelted micrometeorite is a grain of something else, extraterrestrial? One of the real key pieces of information to let us know that it's extraterrestrial is this thin rim that they develop on the outside of the particle, which we call an igneous and a magnetite rim. So it's like a paired, there's an outer layer of magnetite, and then within that, an inner layer of glassy silicate. And those features form by surface melting. So even if the whole particle doesn't melt, a very thin layer of surface melt forms. And that's critical for us to be able to say that this particle is dust in space, rather than just a meteorite that fragmented at the Earth's surface.
So it would also be good to ask you about the work you do on bigger meteorites. Normal meteorites? I don't know what you call them.
Yeah, maybe micrometeorites.
As part of your postdoc project. So I guess you're kind of looking at the same sort of problem, looking at asteroids, but using different samples to study them.
Absolutely, yeah. So in a way, looking at meteorites can be a bit easier because, as we said, there's a lot more material to play with, and they're less affected by atmospheric entry. So a meteorite might explode in the atmosphere and develop a fusion crust, but there are large sections of the meteorite that are even just visible by eye, have clearly not been heated during atmospheric entry. And that means we can rule out those processes immediately. So what I'm looking at is a class of hydrated meteorites, hydrated carbonaceous chondrites. And these are the CMs and the CYs. And those are closely related to the COs, which are a dry group. So what I'm trying to do, the main project I have at the moment, is taking this dry group of CO chondrites, adding some water, and trying to reproduce the textures, the minerals, and even the oxygen isotope composition of those hydrated groups. So in practice, what that means we do is we take a CO that is very well characterized, that lots of people have studied before. In my case, a meteorite called Kainzantz that fell in Russia, I think a very long time ago. And then smash it up into small chips, put those chips in little reaction vessels with certain variable amounts of water. So one of the main things that I'm interested in testing is how the amount of water controls the aqueous alteration, the alteration of these bodies. So what we summarize that as what we call the water to rock ratio. And that might vary anywhere between 0.2, which is very little water, all the way up to potentially 1, which is equal volumes of water to rock. And so, we've got lots of different reaction vessels, essentially, with the same amount of meteorite, but different amounts of water in. And we seal those vessels and we put them in an oven and heat them up to temperatures that we think, based on other people's work, other people's research, are probably the temperatures that we're operating on those asteroids. And those are, for me, the temperatures I'm exploring are 50 degrees and 150 degrees. And then we alter them for a very long time, maybe somewhere like 90 days. We open up those reaction vessels and look at the products, and trying to see how those variables that we've been playing with affect the end product. And at the moment, during the lockdown, this is where I'm at. All these reaction vessels are in long-term, high-temperature ovens, and they're hopefully reacting away while we.
That's really cool.
Out the pandemic at home.
How do we determine how long-term is long enough for that sort of process to happen?
Yeah, this is a real tough question because it could be days, it could be years, it could be thousands of years, the duration of alteration on these asteroids. And obviously, we can't reproduce those longer ends of that alteration timescale. So we don't really know what to expect when we open these up in terms of how much alteration has occurred. But mainly I'm interested in the style rather than the amount of alteration. So even if there's been a very small amount of alteration, it's the types of minerals that are being produced and types of oxygen isotope signatures we're seeing in the altered rock that I'm interested in. It would of course be great to reproduce them exactly, but my hunch is that we won't be able to do that. But one way that we can also speed up artificially, make the reactions happen faster and therefore simulate longer alteration timescales is by powdering the rock. So when we produce larger surface area, we can increase the speed of reactions.
So you're effectively sort of recreating hydrothermal systems potentially that might be occurring on the CO parent body. Is that basically what you're doing?
On the CM parent body.
CM, but yeah, sorry.
Absolutely. This is exactly the kind of idea behind the project, is to simulate those conditions that we think operated on asteroids in the early solar system. And so this is really some of the first geology that was happening in the solar system. And what I mean by that is kind of chemical reactions on rocky bodies. And we think that a lot of these rocky bodies would then go on to be the building blocks of planets. So there might have been 100 or so 100-kilometer diameter planetesimals, and these bodies ultimately impacted each other to form the later planets that we see, Venus, Earth, and Mars. And so we're interested in that kind of early geology on those systems. And specifically, my project is interested in the conditions. So what kind of conditions we're operating.
That's so cool. Oh, so are your experiments still ongoing now?
They are, yes. So the initial plan was we were very ambitious because we wanted to explore the constraints of temperature. So we wanted to do 50, 100 and 150 degrees. The water to rock ratio, so the amount of water, and we were going to do 0.2, 0.4, 0.6, 0.8 and 1, so different ratios. And also the oxygen isotopes, so the composition, the isotopic composition of that water. And so we've got water with different dopings, so different amounts of heavy oxygen in it. So there's lots and lots of variables that we're playing with, but we probably won't be able to explore all of those in the same way as we initially hoped, because the experiments are now going on for much longer. So the idea was you have a limited number of ovens and reaction vessels. You run one batch, then you run a second batch, then you run a third batch. We'll probably run fewer batches, explore fewer variables, but by running them for longer, we hope to see more, or for those changes, those effects to be more obvious. And so that's the position we're at now.
Yeah, that's cool. Do you think, would you expect pressure to have much of an effect on this as well, or?
Potentially, yeah. So the pressure on these parent bodies, especially as they get larger and larger, is not insignificant. And pressure does affect all of these reactions. On a very simple basis, higher pressures can promote faster reactions, but they can also stabilize minerals which are otherwise unstable at lower pressures. That said, we don't expect the pressures on these asteroids to be extreme, similar to, say, the deep Earth pressures, things like subduction zones. Compared to that, they're very low pressure. So that's one of the variables that I've decided to avoid controlling.
Keeps life simpler in the lab too, I guess.
Exactly, yeah. But because we know the volume of the reaction vessels and we know the temperature, you can use a simple kind of ideal gas law equation to work out the pressure those reactions operated under.
So you also mentioned CY meteorites in that before. So we were speaking to Ashley King about that because I believe he had a paper on that recently. Would you mind talking through where that comes into the project and maybe a bit of background on them?
Yeah, absolutely. So while these experiments run, they take, in terms of academia and research life, they take a long time to run. And so you want to have something else to be playing around with and exploring. And so one of the other water-rich groups of carbonaceous chondrites that I'm looking at are the CYs. And these are kind of like a new group that was originally proposed by the Japanese research teams in the 1990s. And that kind of argued that they should be considered a new carbonaceous chondrite group, the 9th carbonaceous chondrite group. And then they were kind of like largely forgotten about. And then last year, our team at the Natural History Museum, mainly driven by Ashley King, did lots of new research on the CYs and came to the same conclusions that they deserve their own classification as a distinct group. And so although they look superficially very similar to CM and CI carbonaceous chondrites, so they're hydrated and then they've been thermally metamorphosed, and they have very similar minerals and textures. One of the very distinct differences is that they have significantly higher sulfide abundances. So the sulfide contents in the CYs reach up to 30 volume%, and go down to as low as maybe 19. So that's much, much higher, up to 40 times higher than the concentrations we find in CI chondrites. And that's a really unusual feature. And one of the other distinct features of the CYs is that oxygen isotope composition is much heavier than all other known groups. And this was known even in the 1990s, but it was uncertain whether their heavier compositions were a product simply of the thermal metamorphism that they'd experienced. So one way you can get heavy oxygen isotopes is by having lots of this heavy, primitive outer solar system water present in the body. But another way you can generate heavy isotopes is through metamorphism, kind of boiling off the lighter isotopes and allowing them to escape the parent body as a steam or a gas or something like that. And so it wasn't clear initially sort of how they had got that heavy isotope group and whether that was an artifact of that formation or a later alteration process on the parent body. The CYs have a whole bunch of other unique exotic minerals, what we might call accessory phases. So they're present in low abundances, but they're unusual because we don't see them in other groups. And the most interesting of these is a phase called periclase, which is actually a really simple mineral. It's a magnesium oxide or iron oxide, so some mixture of the two. It's kind of like a solid solution. And we think that probably formed from the decomposition of carbonates, the thermal decomposition of carbonates during metamorphism. But in the CYs, these periclases are very big, well-developed euhedral crystals that are kind of maybe lozenge-shaped, like a flattened circle, or big cubic kind of square-shaped grains. And so certainly their formation, how they formed is uncertain, but we have some ideas that they might be related to metamorphism.
That's cool.
So the CYs look like they're their own group in their own right. They have unique characteristics. And there's a small number of them at the moment, maybe 9, and they appear to come from only 2 different places on Earth that we can. So the Yamtro Mountains in East Antarctica and the Dhofar region, which is a desert in Oman.
And have people been quite accepting of this new group, or have there still been a few diehards out there that refuse to accept that this is the case?
I'm not really sure, because it takes time from when a paper comes out till you see the responses to that paper. So the paper came out sort of midway through 2019. And I'd say that it's been fairly well cited, implying that people sort of broadly agree with it. And from, what should we say, anecdotal feedback, hearing other people, I think mostly, yeah. But it is not, the group, the CYs are not officially recognized by the Meteoritical Bulletin and the classification, the nomenclature of our community yet. And honestly, I'm not sure exactly how that process evolves to result in this is a widely recognized new meteorite group.
Yeah.
But
it's pretty cool nonetheless, though. We'll put a link to some of those papers in the episode description if anyone wants to read a bit more about them.
Cool, thank you. That is most of everything I'm doing at the moment. I completely unrelated to everything else. I'm also interested in looking at comets, and so when I was in Pisa, at the end of my time in Pisa, I started working on a project looking at whether comets can be aqueously altered as they pass close to the sun. So this is an idea that's been thrown around for a while in the community by a few people, and is largely sort of ignored, I think, in favor of, if there is any aqueous alteration on comets that occurring in the early solar system, and the heat for that alteration being generated by radioactive decay. So the reason I came to be interested in whether this process is important is because of trying to reconcile that problem of whether micrometeorites come from comets or asteroids. Well, if the astronomers and the people who look out into space say that most of this is coming from comets, and yet the particles we look at look like asteroids, maybe comets and asteroids are more similar than we initially think. And that would require that comets have had interaction with liquid water. And so if they weren't altered in the early solar system, maybe they were altered very recently. And increasingly, we have material among micrometeorite collections, which we're fairly certain comes from comets. It has lots of unique features like high deuterium abundances, deuterium excess, these primitive phases, which we call gems, which are like amorphous silicate, and high organic content. So these are all features we associate with comets. And yet we see small quantities of phyllosilicate present on these bodies. And that suggests they've had so phyllosilicates are clays, hydrated minerals. And their formation requires that the silicate rock has had interaction with liquid water. And so when we look at the population of comets, I said before that a lot of those comets are supplying material to Earth in the form of meteor showers. And so we may well expect some of those comets to be hydrated material rather than the pristine anhydrous material that they're made out to be. And so what I looked at in that study was that some of these comets come very close to the sun. They can get heated up to much higher than I expected, at least, sort of maybe even 150 degrees on the surface of the bodies. And we know that they outgas, sublimate, and lose water. And so if their heating generates gas faster than they can lose it, you might be able to generate subsurface pressure in some of these comets. And then that pressure can stabilize liquid water and allow aqueous alteration reactions to happen in the subsurface of comets over very short timescales, maybe 12 hours, just before that dust is released. And that might explain the observations of some hydrated cometary micrometeorites.
Do the phyllosilicates take a very short amount of time to form, or would the liquid water need to be stable for a reasonable amount of time on the comet?
Yeah, so we think these reactions can happen in less than 24 hours at temperature.
Oh, wow. That's really
around
rapid.
20 degrees. And the reason is because the material, the silicates in the comets, are not crystalline, they're amorphous.
Right.
So they don't really have any bonds to break.
Mm-hmm.
In order to initiate chemical reactions, you usually have to break bonds and then form new ones. Well, in amorphous materials, there's no bonds to break. So there's very low enthalpy, low energy required to generate these reactions. And so there have been some really interesting experiments kind of in the early 2000s, experimentally aqueously altering cometary micrometeorites and showing that they alter extremely quickly. And this is another piece of evidence that suggests that it would be possible for comets to be hydrated fairly rapidly. Again, we're talking about a small amount of hydration, not loads and loads of phyllosilicates, but some amount, perhaps maybe 5%.
Yeah, that's really cool. I guess does that have implications for how different isotope systems fractionate as well?
Maybe. I mean, I'm not sure. I haven't thought about it from that aspect. So that paper's under review in Icarus, and it went down quite well at the first stage of review. And so I'm hoping to hear back soon about that. And fingers crossed, it might be online in a few months.
Cool.
Yep.
Brilliant.
Amazing. Well, is it possibly time for our final question?
I think it might be.
So a question that we ask all of our guests is that if you could be doing something else completely different, either in academia or outside of it, what would you want to do?
Okay, so if I could be doing a completely different job. I mean, I quite like my job, and it's really interesting. If I was going to research a different area and something completely different, I suggested that my passion before was paleontology, and I still am very interested in that. So I think it would be really cool to explore, looking at fossils and something to do with early life. Alternatively, if I'm barred from doing anything academic, I'd quite like to maybe have a go at running a brewery.
Well, that would be quite good, yes.
Playing around with the chemistry of hops and yeast and that sort of thing, and exploring different beers, because you get to use your scientific side and blend it with some creativity, and it's, on the face of it, it's quite simple chemistry that we've been doing for literally hundreds of years. But the explosion in all these different types of beers and these different techniques demonstrate that there's still a lot of capacity for innovation. So
Yeah.
I think that'd be interesting too.
Very noble pursuit, I think.
We've spoken to this many geologists, and I think that's the first time anyone's suggested brewing, which is a bit of a surprise now that I think about it.
Well, my parents homebrew wine, and so I've had I got into that as a hobby about 10 years ago now, I guess. And so I've been making wines, homebrew wines from blackberries and raspberries and things like that for a while, just for interest. And it's you get hit and misses, but it's good fun.
Yeah, that's brilliant.
Good self-sufficient hobby for lockdown as well.
Absolutely.
Making
Exactly.
your own
Yeah.
at home.
So it's the right time for elderflower. So we're gonna go out and pick some, and actually we're gonna make some cordial, so non-alcoholic. But that's a plan for the coming weekend.
Sounds like pretty good, yeah. Excellent. Well, Martin, thank you very much for joining us. That was a great conversation.
Thank you very much for inviting me.
Absolute pleasure. So yeah, once again, we'll just put a few of those papers that you mentioned in the episode description if any of our viewers or listeners want to read a bit more about the subject. But in the meantime, thank you once again. And for all our listeners and viewers, if you want some more Earth and planetary science content, do check us out everywhere on the social medias, from Twitters and Facebooks and Instagrams. We're at Earth Solar System. But until next week, have a lovely time, and we'll see you all very soon. Goodbye.